Hi, so I came across an interesting problem um, this morning or yesterday, and it's this integral above at the top in yellow here. And what I want to do, I don't want to solve this integral again, but I'll show you I found two different answers for this integral, right? I found this top answer and this bottom answer, and these are both equivalent, so they just differ by a constant. That's why I included the plus C here. So what I thought was interesting was just to show how can these things be how can these be equal when we get different coefficients in the front, um, different functions. The inside looks totally different. And so what I want to do is just say how can we go from here to here? And you can actually do it in both directions, but I think it's harder to go from the natural log to the hyperbolic tangent function than the other way. The other way is a lot easier. So what I'm going to do is do the hard way first, and then I think at the end, I'll come back and do it in the other direction. So what I want to do first is I think what we want to do is just look at this polynomial here. Because the key to being able to do this is actually to be able to factor that. If you can't factor that, I don't know. I probably don't really know a good way to do this if I couldn't factor this polynomial. So let's try that first. So let me just rewrite this. We have 2x squared plus 3x minus 2. And so we have that. And then what I want to recognize here also, the roots are going to be a half and -2. And so notice that this piece here is this inside the tangent is like in the form of two roots. So if we plug that in and that in, you see this is in the right form. So we have the tangent with the two roots, and these are the two roots. These are the same two roots of this polynomial that we just factored. Okay. So then what I want to do to this factorization, I just want to do one little change. I want to get it in this format of x minus beta, x minus alpha. So I just want to factor a 2 out of this guy. So what we're going to do is we'll write this. So then we're just looking purely at like the roots without any constants in front, without any coefficient in front. We'll write this like that. Okay, then what I'm going to do, and then we'll just rewrite the square root in this format. So we'll bring this in here. And we have a plus 8x. Okay, I'm going to leave off the plus c because that's just going to carry down, but I'll write it this time. I'll try to write it better than that. Okay. So that's just going to come along the plus c, but I might forget at some point, so that's okay. So the next thing I want to do is I want to get this into a form where I just have the two factors here. I want to get rid of this 2, but I can pull that out. So I can pull that out here and make this an 8, right? So if we pull it out of the square root sign. And then the next thing I notice is that we have a common factor between all these terms. So what I'm going to do, let's just rewrite this again. I'm actually not going to pull out a 2, I'm going to pull out a 4. Oh, put a little parenthesis right there. So we pulled out a 4. And then let me show you. Okay, so this is an important trick. Any factor you pull out, you can just cancel out because this gets absorbed in the plus c. And let me just show you the reason for that is the logarithm rule. So like if you just have something like ln ab, actually let me do it like this. Let's write this like ln ax, where a is a constant, x is our variable. This can be written as ln a plus ln x. And then let's assume that we have an expression with a, because we're dealing with an integral, so we have an arbitrary constant there. This is a constant value and it just gets absorbed into the constant. So we're left with just that. So that's kind of a tricky thing to get used to, is the fact that any like constant factors in the natural log can just be added or removed however is convenient. So that's how I did that and got it into this form. Then the reason I wanted to get it like this, so you notice now we have just a product of the roots. Like we've removed the in the original polynomial, basically what we've done, we have the original polynomial like this. We've essentially divided through by a. And we have something like x squared plus b over a plus c over a. So we have our polynomial in that form. And so but the interesting thing to notice, you may think, why did I want to factor this and end up with a 3/2? But looking at the original polynomial, our b is 3 and our a is 2. So b over a is 3/2. So this value is actually what we want. Okay, so yeah, this is pretty tricky to explain in a way that's going to make sense to everybody. So the next step's even more magic. So a lot of this is going to make sense when I do in the other direction, because what I'm going to do now is I want to factor this whole thing. And I would just say that's not it's not something probably you're used to factoring, so it doesn't really stand out. You wouldn't necessarily know just looking at how to factor it. But the way we're gonna know is, again, when we do it in reverse. I think we're gonna see some of these things. But so right now it's gonna be a little magical. But what I'm gonna say is that expression right there is gonna factor as I'm just taking these the two roots the way we have it broken up. So I'm saying that the square root of each of these separate squared is that. So that's the kind of the key piece there. And what you can do to verify, so if we just multiply, let's multiply that out just so you can see it. So it's like if we square this term, we get x minus 1/2, and we'll square the last term and we get x plus 2. And then we do the like the inner product or whatever you call it. And we're gonna have minus 2 x minus 1/2 x plus 2. And you see that's exactly this term right here in the middle. But see, the interesting thing that happens is if we'll just simplify a little bit, we end up with a 2x plus 3/2 minus 2. Okay, which is exactly that expression right there. Okay, so what I'm going to do, we'll rewrite our whole thing again. So we have minus 2 square root of 2 ln, and I'm gonna give myself some space here. Instead of squaring it, I'm actually going to write it all the way out. Like this. Okay. Oh, wait, that's not really the way I want that. Okay, so we have this big thing right here. We're still a ways off. We don't have it. We're trying to get to a Tanh expression. And oh, let me do one thing here. You might be wondering, how do we go from natural log to the inverse hyperbolic tangent? And let me just give a little formula right here. So we want, in order to use this, we need to get our ln expression to look more like this. Once we have something in that format, we can just do a substitution. But we still have a ways to go because what we have inside here looks nothing like that. So the next trick is gonna seem even more magical or weird or whatever. What I'm gonna do is in the denominator, we're gonna have the same thing over here. But then over here, it's gonna be a little bit different. So we're just adding here instead of subtracting. And so you probably wonder, like, okay, how's that allowed? How can you just do that without changing the expression? Well, when you multiply this out, we'll just kind of do that on the side. And if we FOIL that out, we have x minus a half. The multiplying this way, we end up with minus x plus 2. And then because it's like it ends up being a difference of squares, so the middle terms are going to cancel. So if we just add this together, the x's are going to cancel. And we end up with, I think, minus 5 halves. So again, the reason we can do this is just a constant term. And so all we've done is divided it by a constant term inside the natural log, which again is going to be absorbed into the constant. So this is okay. But then by doing this, it allows us to cancel here and cancel here. So next, this is getting us closer, because remember our goal is to have something look like this guy over here. And we do have a way to do that. What we can do is we can take our x minus a half term and divide top and bottom, divide the numerator and denominator by that. So let's just see what that's going to look like. If I multiply through by that on the inside of the natural log, we're going to end up with 1. One minus square root of x plus 2, x minus a half, over 1 plus x plus 2, x minus a half. Okay. So now we're actually getting much closer now, because we're one difference though is the positive sign is on the top and the negative sign's on the bottom, and we have it the opposite way. But that's actually no problem, as we have our negative sign here, and we can use this to flip this expression. So I'm just going to rewrite this as 2 square root of 2 ln 1 plus 2 is minus 2. So now we have our signs looking the way we want. Oh, sorry, that's not a 2, that's supposed to be a half. Okay. X minus a half, x minus a half. Good. Take a drink of coffee. Okay. So then we're getting really close. What we need though, we're missing this half. So again, a little trick, we're gonna just multiply. What we'll do is in here, we'll multiply by 2 and divide by 2. So I'll just write that out. What that's gonna look like is 4 over square root of 2 times a half ln 1 plus x plus 2, x minus a half, 1 minus x plus 2, x minus a half. I should find a way to write less. That's a lot of writing this over and over again. Let's see. Okay, so then this is in the exact form that we want. Okay, now we're at the point where this really matches this guy, and we can do our substitution, where our x value is going to be this big square root term. Okay, so what we can do next is rewrite this in a nicer looking way. It's going to be 4 square root of 2 ln square root of x plus 2 x minus half plus c. And you'll notice that's exactly, I hope it's exactly, or else I'm going to have to do more work. Yeah, that's exactly this right here. Okay, so we did, I think the interesting thing here is there's like 3 steps that are, I don't know what the word is, not very natural, or you wouldn't really, not that easy to see some of these steps. But that's why I'm going to do this. I'm going to do this in the other direction now, I think. Yeah, I'm going to do it in the other direction in order to, oh wait, what did I do? Sorry. This is a tangent right here. Yeah. Inverse hyperbolic tangent. And this isn't an absolute value. This is just a parenthesis, or you don't even need a parenthesis.